We are going to do like a little workshop about the fuzzing engagement I did with Euler for the EBK, playground vaults, and the rewards system. So a little bit of background, quick. I'm the founder of Enigma Dark. It's a company, auditing company I have with Mark Weiss. He's on the audience as well. And I'm an independent security researcher. I've been doing this for quite a while. You have here a QR. You can scan it quickly. It goes to a GitHub repo with all the resources we need for the talk. So if you can scan it, it's just links for the different suites and installation for the Kidna. I'm sure everyone got that. Perfect. Okay. So yeah, a little bit of the contents of the workshop. I will do a little bit of an introduction about fuzzing. Essentially, just overview, because I know not everyone knows about fuzzing or like the techniques. Then we will go over to the EVK invariant suite I built for Euler, and then we will analyze a few of the properties that I think are the most interesting ones and are very related to what the Euler team has been talking the whole morning. And then I will give, if we have time, I will give a little bonus alpha tips for the participants of the contest, so you can leverage the suite into finding more issues or weird edge case issues that not manual review auditors will find, mostly. So what's fuzzing essentially is just providing random inputs to a program, in this case a smart contract in the blockchain, in the Ethereum blockchain, and then we monitor crashes, states between variables, etc. We are using it's in my left, the stateful fuzzing for this suite is what I normally use, and basically it simulates the most user like experience, but randomly generated by the computer. So instead of doing just like you are pre-used, I'm sure you are used to Foundry fuzzing. It's just randomizing inputs for a test. So this just makes like a chain of tests, let's say, completely random. All right, so now that we know what's fuzzing, ideally we will approach how the structure of the suite works for the EBK and of course the other two suites. So normally what we do with fuzzing, in order to, I call it weaponized fuzzing, is like making the most out of the fuzzer. In this case, it's Echidna and Medusa. We will deploy the whole protocol, just like we do in test in Foundry. And we set up a set of, we call it the tester. And what it is just a contract with a few modules inside, so everything is like a monolith. And the fuzzer only has to call these functions on the handlers, and the tester will handle all the calls to the respective contracts. So we can have, instead of fuzzing just one contract, we can fuzz a complete set of contracts, or in this case, a protocol, a module of a protocol, a part of a protocol. The approach is stateful, as I said, handler based, what I just explained, and reduced bias. What I mean with this is, instead of letting either the developers or me, in this case, narrow all the inputs, because like in a UIN 256, the inputs are massive. Since the fuzzer are coverage guided, we let the fuzzer find the best inputs mostly, most of the times. As I said, I used Echidna as the main tool, and then for some parts I tend to use Medusa, but lately I just find myself using Echidna more. So if you are going to run the suite, I recommend using Echidna. There's the three suites that you can check out. The one for the EBK, the one for the EBC playground. It's not in the scope. I think it's not in the scope for the contest, but it's really interesting to check how that suite is built. Yes, it's built more modularly, like the rest of the protocol. And then the one for the rewards. And we can jump straight into the, how am I doing with time? Great. Yeah, okay. We can go to the suite. I should do like probably more soon. Yeah, maybe. Not sure, but maybe I can do it. Can you see it? Yeah, haven't done it, never, so. Theme. Sorry. That one, light. Perfect. Thank you, Mick. So you can see it now. Okay, so yeah, like I mentioned, everything is behind the tester. Tester is just the monolithic contract that the fuzzer calls. We are inheriting invariants. Invariants are the implementation for all the rules. This is what the echidna, in this case, checks, and it will call these functions between all the states. So it does two things in theory. It does it calls a random set of functions of the tester, and then it checks for these special calls between transitions. So it checks the states between every transition. So we got this, and then we have two sets of modules, let's call it more. We have the handlers. For the handlers, we have they act as a proxy between echidna and the protocol. So we have a handler for EVC. We have handlers for all the set of modules. I try to build it pretty modular. So we can have, since Euler is super modular, we can have a different handler for each module, essentially. So we made sure that these are covered, that Echidna covers or mostly, I mean, from 95 to 100% of the protocol, because there are some parts of the protocol that we cannot reach with fuzzing. And we also have simulators, areas, for example, for a donation attack. So the fuzzer takes into account donation attacks. Since since Euler has, it does not use balance of, it uses like internal accounting. We don't really have a problem with this. Then we can go to the invariants I just said, and then we have another type of invariants that are called, I like to call them, I have it spec'd out here. We have two types of invariants, essentially. We have the invariants that are checked between every call, and we have post conditions. That I like to explain this like we save some state before a call, we do the call, and we compare the state right after the call to the state previously. So we can check these are global. These are in theory more difficult to come up with, and there are few of them. And post conditions, there are a lot more, and mostly every invariant, every property that you will come up with is going to be a post condition. So post conditions, we have, I kind of divide them both in two types, global post conditions. Global post conditions are ones that every call, no matter if it's a borrow, repay, whatever call, should hold. So we are not, that's why they are called global. We are not filtering by type of call. And then we have handler-specific post conditions. I will show you later, for example, on liquidations, I have some properties, I have built some properties that I only want them to be true on liquidations, because there's no point of checking a property that you hold on liquidations, but on a deposit, for example. So once we have this understanding, we have some kind of hooks. So we store values before the transactions, and we store the values right after. And we compare a set of post conditions. This will be the global post conditions between both. We will see later in a bit more detail all these what I mean. And everything is inherited into the tester. We aggregate them here, and these are the global post conditions, like I said. And then we have the invariants. We can take a bit of the tests, the functions that were echidna underscore were like the wrappers for these assertions. Essentially, everything is an assertion, but depending on where you check it, is a postcondition or an invariant. So we can go straight into checking which invariants. I have marked a few that are very, I think are very interesting to remark. We have quite a few. So in all of them, like the protocol, like the handlers are divided in some kind of modular compartmentation or something like that. So this one, for example, we are checking that the snapshot should be reset after every action. So what this essentially means is that since invariants, this will be a global invariant, because since invariants are checked between actions, this invariant that is right here, it should be here. We are checking that it is 0 on the invariant. So between actions, it is always reset to 0. This one is trivial, but for example, we can go to this one. Total supply, on all states, total supply should be equal to the sum of mint shares plus accumulated fees. So in order to check for this invariant and to let the fuzzer break it or try to break it, we have to have a set of ghost variables. On each handler, for example, if we go to the mint handler, you will see that there's a function that says increase ghost value. So what we are doing essentially is letting the protocol work, but of course I'm saving variables, I'm saving states on the handlers, so I can track the mint invariants. So essentially the sum of all shares balances, all the minted shares, plus the accumulated fees, plus some extra balance from the fee receiver makes this invariant be true across all states. One more invariant, for example, I think these are pretty common, the token invariants, vault invariants, but what are really interesting, we have here, of course, I think Doug from the Euler team sent me a set of invariants from A16 set, and we implemented them into, so they are for Foundry, so we made them be able to work with Echidna. And we have, these are just like, they check that the implementation of 4626 volt follows mostly the standard. So we have checks for reverts. How we do checks for reverts? So in order to do checks for reverts, on an invariant, we do a try catch. In the case of a catch, we make the invariant fail, and we will get, in Echidna, we will get a warning. And I will check the warning, I will debug it, and find in which state the invariant has broken, and we are not compliant with the 4626, for example. We have a lot more. These are really interesting. You may want to take a look into this. It's just round-trip invariants, a set of predefined calls, and after, for example, the amount you get after depositing an amount A and redeeming should be smaller than A. So you cannot gain assets from deposit and redeem. And these are checked in another way. These are like post-condition invariants, like I mentioned. Then we have the borrowing module. For the borrowing module, essentially, you will see that is the module with more invariants. We check that, of course, the total amount of borrows should be always bigger than any borrow from any account. We have a set of actors that the Echidna uses, and we can, in a for loop, check those. You will see those if you go to invariants, you can see those here. We are iterating through the set of factors that we have set up in the configuration for Echidna, for example. And then let's go back to invariants spec. This one is really interesting. The controller cannot be disabled, never can be disabled, the controller of a vault, without if there's any liability on that account. So if I have some debt, I cannot disable the controller. For example, every implementation this is like a bit of improvisation when you are making these functions. You'll try to make those the most abstract possible, but in reality, you come up with different types of implementations for invariants. So if user depth before we have those hooks, I'm saving all the variables outside on the handler, so we have more flexibility. If user depth before is bigger than 0, the controller after the call should be enabled, true. So this invariant will hold. If this is false, the invariant will break and I will get a warning on a Echidna. If I have coverage, of course. Another one, for example, can be, this one is really interesting. We found a pretty interesting bug with this one. There's on lending protocols, normally they say that the easier the repayments, and repayments should always work. This way you avoid having a lot of possibilities for bad debt, we'd say. So we are doing another try-catch here. So not a try-catch because we are doing it from an actor. You will see I'm not explaining this right now, but we are proxying everything through actors because Echidna uses the HEVM and it works really bad with pranks and start pranks. It doesn't implement the start prank, for example, so we work with actors. It gives us more flexibility. So we assert success. So in this case, we weren't, in some random specific scenario, we weren't getting success. And why? So it was because when you can see here that is this other report. Yeah, you can see here that invariant VM, invariant P from the borrow module, a user can always repay debt in full, was breaking. And why it was breaking? Because when the supply cap was, imagine the supply cap is at 100 and it was diminished, like it was lower. If there's a check, I think Darek explained it earlier, that you can never supply when, if we already have like a supply higher than the supply cap, we can only go lower. So we could only repay, we can only withdraw. In the case of a repayment, some rounding error was making, in this case that the supply cap was less than the actual supply, one rounding error by one way was making the repayments DOS. So this, in theory, could be really bad for like in the case of bad, you can get bad debt really quickly if you have like DOS on repayments. So yeah, we found this and we fixed it. The Euler team fixed it, and we can run. The good thing about fuzzing is that after fixing it, we can run again the suite and make sure it doesn't break in that case, because we are saving like a lot of coverage reproducers, so we can mimic that scenario really quick. If it broke once, it's not going to take like a day to break again. It's going to take a couple minutes if we already have the coverage. So yeah, that one's one. That one's one of my favorite ones from the suite. And we can also go to one more regarding liquidations. I think like Darek mentioned, you can only a liquidation can leave a healthy account unhealthy. So the only way to leave an account unhealthy is through liquidations. This one, I'm not sure, but I think Michael came up with this one. If debt socialization is 0, the exchange rate should increase, or at least be equal. It should never decrease. Yeah, it's like exchange rate and exchange rate with a little comma over there. And then lastly, only liquidations can deteriorate health score of an already unhealthy account. We have over here, we try to build the most generic invariants possible, but sometimes, like in this case, you have to divide them. So we have liquidations for an account that it's already healthy, but here we have liquidations like for an account that is unhealthy. So the only way to deteriorate the health score of an unhealthy account is again with liquidations. And there's a couple more worth mentioning. These are back in the days when I was doing Certora contests. I found myself doing a lot of these checks. essentially, there's some variables in the protocol, like the interest rate accumulator, the last interest, the accumulator update, the timestamp that the protocol is last updated should always increase. So we call that monotonically increases, and we check that. How we check that? We check that through a post condition, of course, because we have to check the state before every call and after every call. So we check it here. It's a global post condition. So after every call to a handler, this is getting checked. So we know that the accumulator, either by rounding errors, by anything, can't decrease, can only be equal or increase. And I think with time, regarding time, how I'm doing. Okay. That's also interesting, and yeah, if like we have time, you can check everything out of this. It's on the, so the QR will have sent you here, so you can go to the suites, to the list of suites, to Ethereum Vault Kit. You can go inside, it says here, inside the test folder and invariants, and you will check it out, all the invariants. And you can, I will give you now some tips for the contest. If you are auditing, I think it's pretty good since the suite, the suite is already built. So if you are auditing and you come up with some scenario that you will want to check, or some property that comes, or post condition that comes to your mind, you can always try it and test it out. So we can go again to the presentation. Yeah, so basic fuzzing tips for the contest. Avoid oversimplification when building on top of the suite, like I said. First of all, make sure that the invariant, if you are going to write invariants, I suggested that the invariants have been reached. It's normal to code, and since a key the behavior we have as testers are when a test crashes, it will show a warning. With Echidna and Medusa, that doesn't happen. Usually, you don't get nothing. You have to check for coverage first. So if I make a handler for a repayment function, I will have to check on the coverage files that I have coverage on all the repayment function. Okay. Then avoid mocks as much as possible. You will see that on the suite there's mocks because there's some behavior that has to be mocked. But all those mocks are randomized as well. So we have on the suite we have simulators. So essentially, for example, the price oracle for the suite that's built on the EBK, it's mocked, but the prices are completely randomized. So and this made us find a bug regarding rounding directions on the calculation of the value of the liability. And essentially, you could borrow one way from different accounts. So yeah, everything that has to be mocked should be randomized as much as possible, or even between some kind of bounds. And apart from that, avoid hard coding values. I mean, if we have the fuzzer, same with formal verification. If we have something that makes checks for a lot of values, avoid hard coding them as much as possible. Then I would suggest you leverage the existing setup in order, instead of just building yourself, because there's enough time to test or whatever on the contest. But I will say leverage this setup and these invariants and tweak them however you want. And I think you will find either you will make the protocol more secure because you will add more invariants. You can also find weird bugs. I hope not, but you can find, of course, weird edge cases. Then, in order to make this possible, you will have to know a bit more about fuzzing. So I suggest either reading reports from other code bases that have done fuzzing suites like EBTC, the engagement I did with Tapioca, or even all the formal verification reports from Certora. They have a lot of great insights. And then I will suggest you focus on running errors, maybe PsyOps, maybe not. But yeah, they are the ones that I found most common with this technique, that I most commonly find with this technique. So I would suggest focusing on those. And I think I'm right on time, like 30 minutes, perfect. So that's my Twitter, and that should be all. I hope you win something on the contest and secure Euler V2.